Okay, so welcome to this lecture on micromechanics in composite materials. We are to derive the elastic modulus parallel to the fiber E1 today. First, some comments on the assumption we make for this. So we are looking at a simple lamina. That means that it's one layer of fibers embedded in a matrix like this. And of course there could be sort of surrounding layers with fibers oriented in other directions. We are only consider this layer in this derivation, so let's take away the rest. So first of all, we assume that these fibers are perfectly straight and they're also perfectly parallel to each other. The fibers, they are linear elastic. That means they have elastic modulus EF. Oops. And the same goes for the matrix EM. We also can assume that it's only fiber and matrix. There is no boundary layer, so to speak, in between the fiber and the matrix. So we are only considering the matrix and the fibers. And these materials, these constituents, the fiber and the matrix, are assumed to be isotropic. And of course we assume that there is a displacement continuity and force equilibrium. So we now take away this layer, and we also take away this layer and go for a new one. So we start fresh. So we said that we had one layer of fibers embedded in a matrix like this. So first a word on the coordinate system. So we say that this is orthogonal coordinate system with the directions 1 and 2, where 1 is parallel to the fiber and 2 is perpendicular to the fibers. And then of course we have sort of a thickness direction which we denote 3. So we're going to derive E1, which actually going to turn out to be the elastic modulus of the fiber times the volume fraction of the fiber plus the elastic modulus of the matrix times the volume fraction of the matrix. So this is sort of where we will end up after this short lecture. Okay, so the fiber has elastic modulus EF and the matrix has elastic modulus EM. So let's take a cut here and look from the side. So we will have a unit cell that looks like this. Where the central part is the fibers, and these two parts are the matrix. So this is then the one direction, and this is direction 2. Or so sorry. So we go, that is of course 3. We'll look upon it like this. Okay, doesn't matter. So let's assume that we deform this unit cell here. So we imply a deformation delta here. So the strain then in this unit cell, E1, epsilon 1, is of course the deformation in this direction divided by the length of this unit cell. So we have some length of this cell like this. Okay, but we can also see that if we're going to assume that this is parallel, it deforms equally, then the strain in the one direction is of course the strain in the fiber, as is the strain in the matrix. So this is the most important assumption in this derivation. Okay, how about the stress? Well, the stress in the fiber is of course the elastic modulus of the fiber times the strain in the fiber. And the same goes for the stress in the matrix, is of course the elastic modulus of matrix times the strain in the matrix. Hooke's law. Simple enough. Okay, so let's consider the force equilibrium here. So the stress in one direction time, well, the load we implied here, the load we put on this to create this deformation, P, is of course the stress in this homogenized material, sigma 1, times the cross-sectional area. So we have some cross-sectional area here. So it's the height times the depth of this. So if the depth is 1, sort of the height and area is the same. So, but because of force equilibrium here, we can now say that the stress in the fiber times the area of the fiber plus the stress in the matrix times the area of the matrix is balanced out by this. Okay, but what we now know that we can put this in here, so we have the EF epsilon F times the area of the fiber plus epsilon m times the area. But the area of the matrix here, so the area of the matrix and the area of the fiber, that could be considered as a so we have the total area is of course made up by the area of the fiber plus the area of the matrix. Okay, but if we look at the portion, we divide this by the full area like this. That means that we can this is sort of area fraction or volume fraction if you so want. So this is then the volume fraction of the fiber and plus the volume fraction of the matrix is 100%. That is 1, of course. So if we now put this in here, we can see that we will end up having, and this is of course the elastic modulus 1 times the strain in the one direction, right? That means that if we put this in this equation, so then we will have the E1 times epsilon 1 equals EF epsilon F times the volume fraction of the fiber plus EM epsilon F volume fraction of the matrix. But we also said that the strain in the two constituents is the same as the homogenized sort of part of this. That means that these can disappear, or they are the same, meaning that the elastic modulus in one is EF VF plus EM VM. And that, sorry, the last part here, so we see, you of course see that we arrived at the equation that we were looking for. So if we now look at some diagram, the E1 over volume fraction fiber, so here we have 100% fiber, and here is no fiber, it's only matrix. So if you have only matrix, of course the elastic modulus is then the same as the elastic modulus of the matrix, and in the same way where we only have fiber, then this elastic modulus would be the same as the fibers. And this one, as you can see, is a linear function. So, like that. So that was the derivation of the elastic modulus parallel to the fiber for one single layer of composite. Okay, thank you.